Hi everyone, my name is Shreya Sinha, and I'll be presenting on the axiom of choice today. Just what it is, some of the justifications on why we use it in mathematics, and some of the quote-unquote paradoxes that it results in. So the first question that we really have to ask is, what are axioms? And axioms are just statements that are taken to be fundamentally true and serve as a basis for our mathematical systems, for our proofs and our arguments. As you can see in the picture, they're what we eventually leads to definitions and then finally proofs. The importance of axioms is that all of mathematics rests on them, and so it's very interesting to see what happens when you have different combinations of axioms, what kind of mathematical systems they create, as well as what happens when you have either too many or too little. If you don't have enough axioms, you can't really prove anything, and then your system isn't interesting. But if you have too many, you can prove everything, and that's also not really interesting. In addition, you have to be careful about what kind of axioms you use in combination with the others, because if you eventually end up with paradoxes in your system, then by the rules of logic, all of your statements can be taken to be true or false, which makes your system entirely useless. So it's really important to look at axioms and understand why we justify certain uses of axioms along with other axioms. And so that leads me to the axiom of choice. So I guess our next question is, what is the axiom of choice? And all it really states is that for every set that has non-empty sets within it, it has a choice function. So on the graphic on the right, you can see these 5 groups of objects. So circles, triangles, pentagons, hexagons, and a square. Take this to be your set X. Within this set X, you have these 5 smaller sets. And all that the axiom of choice really says is you can take one element from each set and create a new set at the bottom, down here with the red circle, the green triangle, so forth and so on. This is your choice set. And so it's very simple to find a choice function for a finite number of sets within your set. All you have to do is explicitly write it down. So for this example, since we only have 5 sets within X, all I have to do is write down that I'm going to take the red circle from the first one, the green triangle from the second one, and so forth and so on. It's also possible, and it's been proven to be, for people to be able to find choice functions for a countable infinity of sets within this set X. That's also okay. But the problems arise when there's an uncountable number of elements. Does that choice function actually exist? The axiom of choice states that it does. You don't have to prove that it exists. You don't have to prove that. You don't have to show what the function is. All the axiom of choice does is that it exists, and you can just assume that to be true. Here we go. So the next question as well, how do we justify using this axiom? How do you justify an axiom at all if it's the basis of a foundation in mathematics? There isn't really anything underneath it that can lead to it or prove it. So what are our criteria? So firstly, I want to introduce the Zermelo-Frankel axiomatic system, which is just a mathematical system that uses 8 other axioms that are commonly accepted as the basis of mathematics. They've been pretty much accepted across the board as, okay, this is our universal system of mathematics. And now, if the axiom of choice ever contradicted this system, we could just totally forget about it. There wouldn't even be an argument to use it. Like I said earlier, if it contradicts the system, we eventually lead to paradoxes, which aren't useful. The system wouldn't be useful at that point. However, in 1938, Kurt Gödel proved that it's not the case that it's inconsistent. You can have fully consistent systems without paradox, that respect both the ZF axioms as well as the axiom of choice. Then, in 1965, Paul Cohen proved that you could have systems that respect the ZF axioms as well as the negation of the axiom of choice. So all that really means is the axiom of choice is independent from these axioms. These axioms do not imply the axiom of choice, and the axiom of choice does not is in no way supported by these axioms and is no way negated by these axioms. So the issue of consistent systems coming out of these axioms is not our issue anymore. Now we have to talk about intrinsic and extrinsic justifications for the axiom of choice instead. So one way that we can talk about what is natural and logical for a system is just that. What are our motivations? How can we best represent our reality? With mathematics, do these axioms truly help us do that? And so those are intrinsic justifications, the more kind of what seems natural and logical. And the idea of choice, in some ways, is very natural and logical. You and I make choices every day. It's very easy, again, in that first example with the shapes, to pull shapes out of those individual sets and create a new set out of it. That doesn't seem unnatural in any way. So I will elaborate a little bit further with a couple examples later. Extrinsic justifications, on the other hand, are to think about how do the axioms lead to specific results that we want to see. Are the results good? Are the results limiting to our system? How does the axiom of choice lead to certain results that are fundamental to other systems of mathematics? Those are extrinsic justifications. And again, I will go into a couple more examples on the next page. And so we're going to start with a couple intrinsic examples first. And so there was a famous mathematician named Bertrand Russell, and he came up with this thought experiment. So in the picture, as you can see, there are a bunch of pairs of socks. And so we're going to first imagine that there's only this many pair of socks. There's a finite number of pair of socks. And every pair of socks has a left socks and a right one. And so if I were to pick a choice set from this pair of socks, and every pair is one of my subsets of my larger pair, of my larger sets, my sock drawer, then it's really simple. All I can say is, okay, give me every right sock. Every right sock is in my choice function, in my choice set. Great. Or if I could pick the left one. It doesn't really matter. The point is that there is an explicit choice function. And again, if there was a countable infinite number of these pairs, I can still say, pick the right sock from every pair. Even if there's an uncountable infinite number of socks, I can just say, give me the right one. And that's a choice function. That's 100% fine. And so for something like labeled socks or shoes that do have a specific label or designation to them, that's 100% fine. I don't need the axiom of choice. I can just pick it. However, if I have an uncountable infinite number of pairs of socks and I remove the left and right labels, then there's no way really for me to order these socks. There's no way for me to say, okay, always pick the left one or always pick the right one, because these socks no longer have those labels. The axiom of choice still allows me to do exactly what I've done before and have that choice set. And it's a little intrinsic in the sense that just because I remove the label, it doesn't mean that anything changed about the socks themselves. It's the same set of socks. I should still be able to pick the same choice set of socks. And so there's not really a disruption to the system in any way. And so that's one of the intrinsic ways of thinking about the axiom of choice. If we can do it for finite sets of unlabeled pairs of socks, then we should intuitively be able to do it for every successive pair. And so the next intrinsic example comes out of the iterative conception of sets. And so what the iterative conception of sets is all it states is all sets originate from a single set of objects. So for example, say my set X is the set on the right, A, B, and C. Then I'm going to take the power set of that set. And all the power set means is I'm going to take every subset possible. So I'm going to have all of my singletons or my single sets of A or B or C. I'm going to have my doubles, AB, AC, and BC. And I'm going to have my full set, ABC. And when you take a power set, you also include the empty set, which is just the set with nothing, which are those two braces next to each other. And so for this set, we'll call the power set, this yellow set, to be set S1 at stage S1. And that our set X is at stage S0, and it's the set S0. So all this says is that, well, if I were to take any of these sets from the yellow set, if I were to take, say, just A and AC and ABC, well, then there's always going to be an element from our original set that has an element from each of these sets. Those can be our representatives. Those can be our chosen elements. So, for example, from the set just A, we have just the element A from the original set. From AC, we can just pick C or A. It doesn't matter. And from ABC, we can pick B or A or C. And so from this conception of sets, which is what a lot of mathematicians and set theorists use, the choice function is so naturally ingrained within this conception of sets that the axiom of choice just makes sense. Every combination of elements exists somewhere in the set, so the choice set exists. And so then we're going to move on to an extrinsic justification. So those were our intrinsic justifications, why it seems natural and why it seems logical. And this is more about the results that we get. So one result that comes directly from the axiom of choice is a well-ordering principle. And all that says is every set can be well-ordered. And well-ordered sets are just that each non-empty subset of that set has a least element, or there's some way that we can order those elements such that there is a first element. And so for something like ordering the real numbers, let's think about that for a second. What's the biggest smallest number bigger than 0? 0.1? 0.01? I could go on, and a lot of people would argue that's just 0, which, okay, true. It has been proven that if you have an infinite number of zeros after a decimal point and then a 1, that's pretty much just 0. However, all the axiom of choice says is that you can reorder them in a different way, in another way, that there is a least element, that there's an element that comes first in this set. And so the axiom of choice is required to prove that the well-ordering principle. Well-ordering needs an infinite number of arbitrary decisions in choosing order. And so this leads to a pretty interesting result. We say that these two, this axiom of choice and this principle, are equivalent. If you prove the well-ordering principle, you can prove the axiom of choice. If you prove the axiom of choice, you can prove the well-ordering principle. They are intrinsically linked. And so if a set can be well-ordered, and so let's think about that for a second. If a set can be well-ordered, a choice function can just be choosing the minimal element of the subsets. There's your choice function. Doesn't matter how many elements there are, you just pick the minimal one every single time. And on a similar note, you have Zorn's lemma. And this is a little bit of the opposite. And all it states is that for any partially ordered set containing upper bounds for every totally ordered subset, it must have one maximal element. So each of these subsets instead have one maximal element. And so that's kind of equivalent to thinking about what's the smallest biggest number less than 1? 0.9 repeating? And so on that note, it's been proven again that that is just 1. It's a bit of a debate, but most people agree that it's just 1. And so again, the axiom of choice says that you can reorder anything, any of these subsets so that you have a greatest element. And then again, your choice function just ends up being that you pick that greatest element every single time. So all 3 of these are intrinsically linked. Again, if you prove 1, you can prove the other 2. And it doesn't matter which one you prove, the other 2 follow true as well. And it's a little interesting to think about what these other principles and this lemma and that principle say for mathematics as well. For anybody who's ever taken linear algebra, One of the first theorems you learn is that every vector space has a basis. Zorn's lemma is crucial to proving this. And if you don't take the axiom of choice true, that assumption is no longer true. And so it's very fundamental to a lot of other fields of math, such as linear algebra, abstract algebra, and topology, and more, that the axiom of choice holds. And so now I want to talk about probably one of the most fun and interesting paradoxes, the Banach-Tarski paradox. And so all it says is if you take a 3D sphere, divide it into 5 infinitely detailed pieces and put it back together, you'll get 2 spheres of the original volume and density. And so what this means is that you can take a P, split it into 5 pieces, and turn it into the sun in terms of size, which is, of course, unrealistic, and it would never happen in our reality for a couple reasons. But it's interesting to think about the proof for a second and understand that it relies on the axiom of choice. Without the axiom of choice, it's not true. And so one may think, okay, well, if I can turn a P into the sun in terms of size, then the axiom of choice is clearly not, it's very contradictory to our reality. If we want to have a system in mathematics that truly represents our reality, then we shouldn't use the axiom of choice. To that, I would say, we don't define this sphere to have a specific volume. We don't define each of those infinitely detailed pieces to have a specific volume, so conservation of volume isn't violated. It's also interesting to think that, okay, well, some other mathematicians have taken further steps to conserve volume in this. And you can do so instead of using topological spaces, which is what the proof uses. You can use locales. However, in the same argument, we have to have 5 infinitely detailed pieces. We assume that matter is continuous, that our universe is continuous, which we clearly know it's not. Atoms and particles are clearly discrete. So this wouldn't hold in our reality anyway. And it's also a little interesting to think that there are a few papers on quantum physics that suggest that there's a link between this paradox and the behavior of particle collisions. And so in that, but again, in that argument, our world is discrete, so why should we even care about using the axiom of choice? It really does say deeply strange things about deeply strange things that will never happen. In our world, we never see infinite sets. We only pretend some sets are infinite, so it makes our lives easier, but that principle only, it never makes contact with our reality. So the reason that we use the axiom of choice and axioms like it is the same reason that we use infinity at all. Everything we've ever seen is finite and discrete. Objects are made out of atoms, and even if space and time aren't truly quantized, our ability to measure them is. But it's really convenient to assume that space and matter are continuous. For example, anybody who's ever taken a physics class or a calculus class knows how powerful things like derivatives and integrals can be. And sure, within those you're assuming that you can have instant moments of time, this point of time that's not discrete, that's not finite. But when we assume things to be that large, our answers become good enough for whatever we're doing. It's why we use limits instead of working with infinity like it's a number. So if we're trying to model anything in the world, really, any infinite set we have to deal with is going to be a limit of finite sets. And we know we have a choice for finite sets. The axiom of choice holds for a finite set, and I showed it to you earlier. So we can always get choice from these finite sets. And as long as we use limits to approximate infinity, to approximate our reality, the axiom of choice becomes very, very powerful. And again, that's the purpose of the axiom of choice. All it says is don't worry. You don't have to explain how your finite sets are assumed to be infinite. You don't have to explain how you're choosing elements. You just assume that it's true. So to conclude, the axiom of choice has many important usages in many fields of mathematics like analysis, linear algebra, abstract algebra, measure theory, and general topology. Many proofs themselves also involve arbitrary choice in order to prove general statements and theorems that are self-evident and intrinsic as well. In these fields, the mathematicians tend to accept Zermelo-Frankel choice axiomatic set theory because of the positive consequences it has. And it's also a very beautiful result to know that the axiom of choice is independent from its from the other axioms within the set, that mathematics is subjective at the very foundations of itself, and that we can pick and choose to figure out exactly how do we best want to approximate our reality with such powerful tools. I would just like to say thank you to Dr. Owen Griffiths and Alex Fisher for running the amazing course that helped me really delve into this topic, to everyone who has participated and had a hand in creating this event and making sure that it was possible, and my families and friends for supporting me. Thank you for listening. And if anybody has questions, I would love to take them now.
Thank you so much, Shreya. And we'll simply open the floor to questions for anyone who feel free to either type it in the chat or simply unmute yourself and raise the question through the microphone. Okay, Shreya, maybe I'll begin with a question that trains a little bit on the last point you made about this being a beautiful result, which I was surprised to hear was followed immediately by so you said something along the lines of you thought it was a beautiful result because it shows how subjective mathematics is. And that's interesting because I would imagine a lot of people within the philosophy of mathematics would find that result, would describe that result using another word, like something like terrifying or unacceptable or something along those lines. Can you expand a little bit more on why you think it's beautiful rather than, you know, vertigo inducing or just repugnant or whatever?
I really do think it's a beautiful result, just because in some ways math is almost like art to me. Like you have many forms of art. You can do it with charcoal, you could do it with paint, you could do it with whatever you want. And all that mathematics really tries to do is answer the question, how accurately can we represent our reality using these abstract notions of numbers and all of this. And so the fact that at the very, very core of mathematics, we have the ability to choose and pick and really see what kinds of systems of mathematics come out of that is beautiful to me, just because of how freeing it almost creates, like the freedom that it creates, and just how creative can we get? What kind of realities can we create out of different combinations of these axioms?
Okay, and I'll just press you a little bit more on that, because you seem to, and I don't think it's an unresolvable tension, but there seems to be this slight oscillation between saying that, you know, we have this great amount of creative freedom, meanwhile we're sort of trying to represent reality, so thinking of mathematics as some sort of representational tool. So how, in your mind, do you sort of reconcile those two ideas? Because a lot of, I think, if you look at some more traditional philosophers of mathematics, they will be typically thinking along the lines of there's some sort of mathematical reality, and maybe the goal is simply to describe that So we're really being dictated by, these Platonic mathematical forms or whatever. And so whatever freedom exists is very much constrained by this passive dictation by the mathematical objects themselves. So I don't know if that makes sense, but do you have any thoughts on that?
It's a little like the multiverse theory to me, that there are these other universes with other laws of physics and mathematics out there. And when I hear about something like the Banach-Tarski paradox, this really unrealistic paradox for our world, it makes me wonder, well, it's a way to explore these other worlds to me, this like the freedom, and just think very abstractly and creatively of how can we think about things differently within our world? How can we think about different things that couldn't happen out in our world? And to me, the ability to make those observations is the most important thing that I get out of, I guess, thinking about these different axioms. And you're right that it is a bit constraining, that maybe you have to look at all of these results and then you realize, oh, you can't use that axiom anymore in describing our mathematical reality. But within using them, I think you definitely find different ways to observe your own reality. And that's the power, I guess, of the subjectivity.
Cool. Thank you so much. That's a really great answer, I think.